Anyway, if you have other questions on the exam, no problem, just let me know. Okay, so basically, let me move forward with I remind you what we are talking about, generation of synthetic hydrological data by using statistical methods. And what I did on Thursday was an introduction to probability, and I defined, to make a very brief summary, what is a random variable. I defined what is probability and what is the probability distribution. And I introduced three probability distributions to you, and in particular, I introduced the Gaussian or normal distribution, the log normal, which is just the logarithm of the normal, and the uniform distribution. And I have one thing to add about the normal or Gaussian distribution. I already said that it's a very important distribution because it's a limiting distribution to which any random variable converges after aggregation. And I also said that in hydrology it's not really very useful because usually we work with fine time scales, and at fine time scale any hydrological variable it's usually non-Gaussian, but still I said this is very useful because by simply taking the logarithm you can reconduce most of the hydrological data to the Gaussian distribution. Now there is another striking property that I would like to put in evidence about the Gaussian or normal distribution. And let me start by making a premise. The premise is that when you deal with a random variable, the random variable has its own probability distribution. If you take a transformation of the variable, whatever, the transformed variable doesn't maintain the probability distribution. So basically, if I have a Gaussian random variable and I take, for instance, the square root of it, the resulting distribution is no more Gaussian. And this is rather intuitive if you think at the log normal, for instance. The log normal distribution is a transformation of the Gaussian distribution, and it's a different distribution. And even if you take the power of, to some exponent of the random variable, like if you take the power 2, if you the power 2 of the random variable, then this is a transformation that doesn't preserve the probability distribution. What about a linear transformation? It's the same thing. If you have a linear transformation of the random variable, like let's suppose that you have a random variable x, which is defined, for instance, in depending on time. And keep in mind that usually when I use a capital letter, I indicate the random variable. When I use the lowercase, I indicate a single observation from the random variable. In statistics, we say a single outcome. So one thing is the random variable, which is a variable, and therefore, for varying t, you obtain several data. Another thing is the outcome, which means that you refer to a specific t, a given t, and then if you refer to a given t, you pick up just a number, one data. And this is called the outcome from the random variable or the realization of the random variable. And usually in the textbooks of statistics, they use the capital letter for indicating the random variable and the lowercase for the single outcome. So if I have this random variable, capital X, I can take a linear transformation defining a random variable, capital Y, which is given by, for instance, a parameter A that multiplies capital X plus a parameter B, which is an additive constant. So this is a linear transformation, and the linear transformation is a very simple transformation which has nice properties, and one may think that the probability distribution is preserved because the linear transformation is not a strong transformation. And the reply is, in general, no, the linear transformation changes the distribution. So, if x is Gaussian, y, it's not guaranteed that it's Gaussian, still Gaussian. The linear transformation changes the probability distribution in general, like any other distribution. Just let me say that if you simply add a constant, you don't change the distribution. Okay? So if you simply add a constant, you don't change the distribution, but if you take a linear transformation like this one, yes. There is only one distribution that is preserved through linear transformation, which is the Gaussian or normal. So, if x is Gaussian, we can say that y is Gaussian with different parameters. Parameters are mean and standard deviation. They are different, but the distribution is still Gaussian. This is an important thing that you have to keep in mind. So, why you should keep in mind this? Because, for instance, an important consequence of what I said is that if you have a probability distribution for rainfall, the probability distribution for river flow, which can be considered according to some mathematical model, river flow can be considered a transformation of rainfall, the probability distribution is different. Unless the model is linear, like the EUH model, and rainfall is Gaussian. So if you have Gaussian rainfall and a linear rainfall runoff model, you get runoff Gaussian. Gaussian runoff. But if you exclude this very exception, Gaussian distribution, then you can conclude that in general the probability distribution changes in hydrology from the input data to the output. This is important for you to know. But again, the Gaussian distribution has this nice property. This has a relevant implication for what I'm doing in 1 hour from now. So this is something that I wanted to highlight.
Please repeat. I have a runoff model full of Gaussian distribution.
Not the model. The model doesn't follow a distribution. The input data are Gaussian.
Okay.
And then you have a transformation model to transform rainfall in runoff. Okay.
And
so
it's linear.
if it is linear, then you get Gaussian runoff. But only if the model is linear and the rainfall is Gaussian. If you have a rainfall that is log normal and the transformation model is linear, you get something different from the log normal in the output. The Gaussian distribution is the only one that is preserved. Okay, that being said, now let me draw to your attention the fact that we already have the means now to generate data under certain conditions. And in fact, you may remember, those of you who attended the lecture on Friday, you may remember that I indeed generated data using R from the normal distribution. And I told you, look, these data do not look like river flow because they are randomly fluctuating while the river flows are much more regular. We have an hydrograph with an ascending limb and then a rising limb, and then a recessing limb. So the data, if you look at river flow data, they are more regular. you see some regularity along time. Instead, the data that we generated were randomly fluctuating around their mean. But indeed, we made a generation. And we made the generation from a Gaussian distribution. I had to specify the average, the mean, and the standard deviation, and the number of data that I wanted to generate. And we used the routine in R, which is called R norm. And I told you that I will explain later to you how this generation is done. The generation is done in a simple way. And first of all, usually probability distributions, and I already mentioned this to you, are expressed in the form probability, either the density or the probability of not exceedance, either the cumulative probability or the probability density is expressed as a function of the data x. Okay? So the probability of a single observation x, lowercase x, is expressed as a function of x itself. In order to generate data, we are not interested in this relationship because we are not interested in generating probabilities. We are interested in generating x. So it's better to express x as the inverse of the probability of x. This is what we need to know. And therefore, through this relationship, if we enter with probabilities, then we may compute the corresponding observation. When you compute back the observation starting from a probability, the observation that you estimate is called the quantile of the given probability. The quantile. And usually, it's easier to use the cumulative probability within this relationship. I will explain to you in 1 minute why it's more useful. So basically, by computing the quantile, we can draw random outcomes from whatever probability distribution. There are some probability distributions that are more easily tractable because they can be inverted analytically. There are other distributions that cannot be inverted analytically and must be inverted numerically. But given that we have a PC with some code that computes the inverse for us, this is not really relevant for our purpose, but you have to know that there are some distributions that can be inverted and others that cannot. The Gaussian distribution cannot be inverted in terms of cumulative probabilities, not analytically. But still it is not clear to you how to make the generation. So let's suppose that instead of using the program, you have to make it yourself. And let's suppose that you have this relationship expressed in an analytical form. So let's make it simple. Still, you don't know how to do that operationally. And the question that is unsolved is how can I generate these probabilities? Because this is what you are missing at this stage. You have an analytical relationship which is the inverse of your distribution, which is available by assumption. But your question now is, how can I generate the probabilities? Let's remember what probabilities are in terms of cumulative probabilities. They are numbers between 0 and 1. Okay? So what I have to plug in here is a series of n numbers, and it's my choice, number of observation that I want to generate. So I have to pick up a series of probability to plug in here. Probabilities means numbers from 0 and 1. And how should these be selected? Basically, what you have to plug in here is a series of numbers between 0 and 1 which are occurring according to a uniform distribution. This is what you should write, and then I try to explain. So here you have to put a series of numbers. How many, it's your decision. Between 0 and 1 according to a uniform distribution. To a uniform distribution. Uniform means, I define what is a uniform distribution. It means that you give the same probability to the numbers to occur in the interval 0, 1. So this is the same probability that you give. So you may say, this is not clear to me, because you may say that, of course, the extremes, by intuition, you may say that the extremes should be more unlikely to reach. Because you may say, okay, an observation that has a probability of not exceedance of 0.9999999 is much more difficult to reach, because it's a very extreme flood or extreme rainfall, whatever. So the intuition could be this extreme value should be simulated with not with the same probability of getting a normal value, a more usual value. So you may think that the extremes should be picked up much more rarely than the values that are close to the average of the value of x. But this displacement is done by the function f, not by displacing the probabilities. The probabilities should be uniformly displaced, and then the function f that concentrates the numbers close to the average. And let me make an example here. So if I draw a normal distribution in terms of cumulative probability, and I have x here and the probability of x here, the probability is included between 0 and 1. And let's suppose that the average of the random variable is 0. How does it look, this distribution? It's asymptotically very close to, for high values, for very low values of x, the distribution has a probability that is very close to 0. So it remains very close, very close, very close, and then suddenly goes up, and then symmetrically, it suddenly goes very close to the value of 1. This is the cumulative Gaussian distribution. Now, what I'm proposing to do is to get random numbers displaced here with uniform probability between 0 and 1. And you see that all these random numbers basically concentrate the values of x in a very close range around the mean. Only when you pick up a number that is very close to 1, you get a flood. And only when you pick up a number that is very close to 0, you pick up a drought. But you know, these numbers between 0 and 1, they fall in the interval with the same probability. But you see that it's very difficult to pick up a flood or a drought because you have to get very close to 1 and very close to 0. Much of the numbers that you enter with uniform distribution will concentrate in a small range around the mean. So basically, the concentration of the values close to the mean is operated by the function f, not by the probabilities. The probabilities are uniformly distributed. I still think that the concept is not very clear to you. To clarify the concept, I give to you a suggestion when you get to proceed. And the suggestion is to make this very simple experiment. Because there is nothing that makes things clear like trying, like making an experiment. So instead of spending time now on reasoning on this figure, I propose to do an experiment. Then you make the experiment, and then on Thursday you tell me if you got convinced, because otherwise, you know. And then for today, let's take for true that you have to enter with a uniform distribution. Okay, so let me propose the experiment to you. And let me write here. Basically, what we did on Friday was to generate a Gaussian data. And you can write, define a variable G data, for instance, in R. I'm writing in capital letters, but of course you know that in R you have to write with lowercase letters, okay? So, what we did on Friday was to generate G data as R norm, and then you have to put a number like 10,000. And then we put 0, 1. And this is the number of data, and we make it here, number of data. And this is mean. And this is sigma. This is the instruction to generate random outcomes from the Gaussian distribution in R. And you already know how to compute the density of this data. If you just write density plot density G data type equal 9. If you write this instruction, you make a plot of the density of the data, and as you may remember, we checked that the data indeed were Gaussian. What we got is a perfect band, a perfect Gaussian band. Okay, but we don't know how this R norm works. So let's try to use the procedure that I explained to you. So let's try to remake this generation. This is a baseline. Let's try to remake it according to the procedure that I just described to you. And then you will see that the outcome is the same. Okay? So basically, just keep this as a baseline. This is your reference. Term of comparison. Baseline is a term of comparison. And let me now do the generation in R according to this procedure here. So, first of all, let's generate the probability through a uniform distribution. distribution, because I told you I have to generate random numbers between 0 and 1 according to the uniform distribution. So let me write G data is equal to R unif 10,000 0, 1. Here 0 is lower and this is upper. With the uniform distribution, 0 and 1 do not mean average and standard deviation. They are just lower boundary and upper boundary. Okay? So basically what I generated here is just uniform numbers between 0 and 1. Uniform again means that the probability is equally distributed. You can write here a plot, same instruction as before, plot density G data type equal line. And if you draw this plot here, you will see a result like this for the density. It's 0, 1, and you will see something like this. It's a bit smoothed at the beginning and the end because the R routine to compute the density tries to smooth it. But anyway, you will see that the density is uniform around the value of 1 here. This is Px. So this is not Gaussian, of course. Now, the next, so there is nothing to explain more here. This is just a random number uniformly distributed. The next instruction has the purpose of transforming this data into Gaussian data. And the next instruction is let's override the variable. G data is equal to Q norm data 0, 1. And this is mean, and this is sigma. What is Q norm? Is Q stays for quantile. Quantile normal. Quantile of what? Of the given probability. And the probability is given by G data, generated through the uniform distribution. So what I did here is generate uniformly distributed probabilities, and then with this last instruction to apply the inverse of the distribution. It's just what I explained to you before. And if the procedure that I explained to you before is correct, now we should have Gaussian data. And in fact, if we go back and redraw this plot, then you will see that the distribution is Gaussian. Displace it differently than here, because here you will have the mean that you put here. So the displacement of the distribution of the two density is not necessarily centered. It can be shifted depending on the mean value that you give here. Okay. So we can generate data already. Just make this experiment, so playing with numbers you will realize how it works. But there is a but, and the but is the problem that I mentioned to you 15 minutes ago. I said these numbers are not regularly displaced, they are just random numbers. And let's be more clear, what's the difference with respect to river flow? I mentioned to you that the difference, I mentioned to you on Friday, that the difference is memory. The river flow is a process that has memory. And the memory is given by the fact that, you know, the watershed remembers its past. So I made the example of the Po River. If I see today a flood over the Po River, then if I go there tomorrow, I'm expecting to see a still very high flow. Maybe it's not a flood flow, but it's still very high, because the catchment has some memory. The memory is a distinguishing property of the catchment. And it's directly related to the behaviors of the catchment. There are catchments that have a very long memory, catchments that have a very short memory. So, what is effective on the memory? First of all, the size. If the catchment is big, the memory is longer. In fact, we know that floods over the Po River last for 1 week. If you have a very small catchment, the flood may last for 15 minutes, which means that the memory is very short. So the size, in this case, matters. And not only the size, but also the geology. And also the presence of snow and glacier. Because of course snow, induces effects in terms of river flows that last for a long time. These numbers that I generated, they have no memory. Any outcome doesn't have any memory of the previous outcome. So this is a problem that we have to solve. We cannot generate hydrological data that have memory, that possess memory, with this procedure. We cannot. We have to devise a different procedure. And this is a bit of a complication. So what is the trick that statisticians devised to deal with this problem? The trick is to introduce a twin concept with respect to random variable. So far we spoke about random variables. Random variables means a variable that has no memory of its past. Or let's say, so far we didn't take into account any capability of the random variable to remember its past. So we have to introduce another concept, very similar, and the idea is that of considering, because, you know, let me turn to the river flow, and therefore use the symbol QT. What is memory? Memory is the fact that if you look at qt plus 1, and if you look at qt plus 2, you have a direct relationship between these two variables, a dependence, which implies also a direct relationship between these two variables. So the idea in statistics is to assume that we have a random variable for qt, a random variable for qt plus 1, and another one for qt plus 2. So at each time step we define a random variable. This is the idea. Each one with its own probability distribution. And then we define a relationship between the subsequent probability distributions. So this is the idea which I am repeating now.
Sorry, could you repeat it?
Yeah, I repeat. So far, basically I defined a random variable. I said that the random variable is described by a probability distribution, but I said that the outcomes are independent, have no memory. So an idea for taking into account the fact that there is memory, an idea which may seem complicated, but you will see it's not. It's to assume that at each time step I have a random variable. So I have a random variable at qt, a random variable at qt plus 1, and a random variable at qt plus 2. And then I define a relationship between the probability distributions. So I may say, for instance, if qt is Gaussian with mean 0 and standard deviation 1, qt plus 1 is still Gaussian, but with a mean of 0.5 and a standard deviation of 0.8. So if I define a relationship between the probability distributions, I can explain the memory. I cannot explain the memory inside the probability distribution. I need more than one probability distribution at each time step. I need one probability distribution, and then